Assalamualaikum and a very good afternoon. Our group, which is group 4, will be present about digital design project report, which is the title is Integration of Home Automation and Security System Controller with FPGA Implementation. So, for our group member, which is Muhammad Syakir bin Muhammad Alim, Pang Wei bin, Muhammad Luqman bin Muhammad Idris, Muhammad Nuzul Arif, and Muhammad Amir Rushdi bin Kamal. Ahmad Kamal, sorry. Next, I will present about introduction. The rapid evolution of technology has led to the rise of smart living with a focus on home automation and security system. The smart home concept driven by advancement like the Cyclone IVE, EP4CE115F29C7 FPGA board or short term is DE2115 aims to overcome challenges faced by traditional systems. This project integrates home automation with a robust security system to enhance scalability, flexibility, and security features. The goal is to provide a comprehensive solution for automated device control, ensuring both security and energy efficiency. Subsystem include is security control, environmental comfort management, and automatic load transfer switching mechanism. Next, our objective is to develop a cohesive system that combines home automation with robust security features. We implement window, fire, and door alarm using sensors like active IR sensor, magnetic switch sensor, and smoke sensor. We enhance user verification with passcode-based door locks. We create subsystem for lighting and HVAC control using sensors like LDR, IR, and LM35 for efficient energy management. We implement a mechanism for automatic load transfer switching to ensure uninterrupted service during power blackout, prioritizing between solar and grid power source. We analyze PWM technique for lighting control, implementing dynamic light, and uh, based on human presence detection.
Hello, and let's have reason for methodology. Okay, first we choose Cyclone IV, which is our FPGA board for versatility, for power consumption, and for programming resources. And next we utilize a bottom-up design for modularity and simplicity for each subsystem, which is our security system control, environment comfort control, load transfer switch control, which design independently for easier testing, debugging, and feature expansion. Okay, next we employed a Verilog HDL for concise hardware description, which we use Multisim Altera, used for simulation and appropriate tool for synthesis and implementation compatible with Cyclone FPGA board. So last we use a top level module which is home automation controller, which orchestrate and subsystem integration. The subsystem evaluate test before integration. System coordination achieved through careful signal interfacing and control logic. So thank you.
Okay, now we're gonna look up for our first VHDL code example. So basically this is the home automation controller. So what I've done here, which is there are some key points regarding about this coding. So the first one is gonna be the entity declaration, which is our home automation controller. Entity has input for clock and reset, and other and of the input and output ports are mentioned indicate that we can add them based on our specific requirement for home automation controller. And then the second one, the second key point, which is regarding about signal declaration. So our signal, which is have been stated in this coding, which is security out, environment out, load transfer switch out, and PWM out, which have been declared to connect the output of the submodule. And basically, these signal are used to pass the data between the submodule. The third key point is gonna be is about installation of submodule. So this code is stated for submodule, which is the security system controller, environment comfort control, load transfer switch controller, and PWM controller. So this submodule represent different functionality of the home automation system based on this coding. The next key point I would like to explain about our port mapping. So the port map statement is connect the port of the submodule to the corresponding signal and ports of the home automation controller coding. So we can adjust the port connection based on the actual input and output ports based on our submodules. And the last one, which is the code have been demonstrate a modular and hierarchy design approach where each submodule has been responsible for a specific aspect of home automation. So this make the code is more readable, maintainable, and facilitated testing of individual component. Okay, now this our next VHDL code outline for the structure of a security system controller. So as usual, you need to declaration of their entity. So our entity is declared with input and output, and which also including the clock and reset. And for our this coding system output is gonna be the window alarm out, fire alarm out, and door alarm out. The next one is the internal signal and variable. What this have done is include the signal for sensor input, intermediate calculation, or any other internal state variable required for the system logic. The third one, as we can see, this coding is the behavioral architecture. So it will indicate that it will focus on describing the behavior of the system rather than its physical implementation. Next is gonna be the empty behavior block. As you can see here, the begin and the end of behavior encapsulate the behavior block where the actual logic of the security system controller is need to be implemented. And and the last one is gonna be the implementing of security system control logic. So it will instruct that the security system control logic should be implemented of this block. So basically, it will involve handling alarm for various events such as window breaches, fire incident, and door intrusion. Okay, the third one is about environment comfort control for this VHDL code. So same, the entity declaration is gonna be environment comfort control, which is clock reset, and for the output of for the lighting system is gonna be lighting system out, and for HVAC, which is heating, ventilation, and air conditioning system, is gonna be the HVAC system out. So both of them is gonna be the output for the lighting system. For our internal signal and variable is gonna be including the signal for sensor input such as LDR sensor, IR sensor, and also we have the intermediate calculation or any other internal state variable required for the environment and comfort system logic. And for our code, this is also the architecture of the behavior. Um, and for the empty behavioral block, we can see the begin and end behavior encapsulate the behavior block where the actual logic of the environment comfort control need to be implemented. And implementing environment and comfort system logic into this coding is gonna be the monitoring sensor, which is the LDR itself, infrared, managing the temperature and controlling the lighting and the HVAC system based on the environmental condition. Okay, moving on to our load transfer switch control. So the first one, the entity declaration. Firstly, for our input and output, we need to be declared, and also we have clock, reset, and input for primary and secondary sources of the voltage, which is primary source voltage and secondary source voltage. And for our output, it's gonna become the load transfer switch out. And also we have the internet signal and variable, which include monitoring the voltage, intermediate calculation, or any other internet state variable required for the load transfer switch control logic. And this coding of the architecture is going to be the behavior, And the implementing of the load transfer switch control logic is gonna be the monitoring the primary and secondary source voltage and triggering the switch based on the predefined condition that uh, that can be changed in this coding. And for the last one of our VHDL code for PWM controller, the key element, the first one is gonna be the entity declaration, which is we have also including the input, output, and also the clock and reset. And for our output for PWM signal, we have declared as PWM out in this code. So the next one, what is our internal signal and variable? It will include signal for generating PWM pulses, intermediate calculation, or any other internal state variable required for the PWM control logic. And this code architecture is going to be the behavioral. And our implementation in this code is going to be the generating pulse for dimming the lighting system or controlling the duty cycle based on the specific requirement in this code.
So, good day everyone. So, my name is Pang Wei Bin, metric number AN200195. So, I would like to present the result for our system. So, from this result, we can know that the 40% of duty cycle design and the 100% duty cycle design are verified using model sim Altera. So, this figure has demonstrated that the output is simulated pulse per 200 Hz, which matching the findings of that study. So the next is the result of the 40% duty cycle on time, which is 2 millisecond, has been shown in the diagram. So the next is the result of the 40% duty cycle simulated at off time, which is 3 millisecond. So it was found that the simulated waveform matched a 40% cycle arrangement. Next is the simulated waveform of 100% duty cycle is also being proved that simulated on time and off time second and 0 millisecond. So in this system, the user can deactivate the alarms except the fire alarm, which activates upon entry. The system can be reset and the fire alarms will triggers on combustible gas rise. Windows alarm will activate with motion and a broken switch, and the door alarm will reset the password. So the correct password will open the doors with a green light. Incorrect attempts will trigger a yellow light. After 3 failed attempts, the system freeze until reset. So the light sensor will turn on the light with a 40% duty cycle in darkness without motion. So if the motion is detected at 100% at night, so the lights will have a 100% duty cycle. The HVAC system will process an 8-bit temperature sensor input controlling the actuators. And finally, the power line defaults to the solar and resets when the reset button is pressed. The relay will keep the default line if both power sources are stable, otherwise it will switch to the grid. This design will ensure the solar battery is in overuse. Finally is the utilization report of the suggested design, which is the top level module via the Cyclone 4 E-base FGPA, which is displayed in this figure. So it has used 32 register, 74 pins, which is 14%, and 162, which is less than 1% logic components in total. The FGPS virtual pin, memory bits, integrated multiplier 9 bit components, and PLLs are not used by this top level module. So that's all on me. I will pass to the next presenter. Thank you.
So for the conclusion of this project, finally, a suggestion was made to include the security, comfort, and power outage avoidance elements into an energy efficient controller. It was possible to effectively create and simulate 200 Hz duty cycle path in order to prevent noticeable light flickering during a dim light event. In terms of further user authentication, automated load switching, a mechanized lighting system with dimming capabilities, and more home device for temperature control, the suggested design improved upon the earlier proposed works. The suggested controller may be used as a control unit of home automation system that offers users a secure and well-maintained living environment while using few FPGA resources. It prevented the services, especially for the internet router and network-dependent device, that depending grid from being interrupted by power blackout and improve the effectiveness of lighting control. It allows the further expansion of the automation system by using the same controller. So that's all from all of us, and thank you.